Welcome to my online course in linear algebra for undergraduate mathematics. Today we are going to discuss about Gram-Schmidt orthogonalization theorem. First is the statement of the theorem. Let S equal to S1, S2 dot be a linearly independent set of vectors in an inner product space X. Then there is an orthonormal sequence T equal to T1, T2 dot in X corresponding to this S such that linear hull of S is equal to linear hull of T. That is, linear hull is nothing but the linear span is known as linear hull. If S is my linearly independent set in X, then this S is either basis of can be extended to form a basis of X. Then by Gram-Schmidt orthogonalization theorem, there will be a orthonormal basis corresponding to this S of this inner product space X. Now proof S is linearly independent, then all SKs are non-null vector. If any one of the SK is null vector, then with its coefficient, non-zero coefficient in linear combination, in combination of S1, S2, dot, this set of vector S is linearly dependent. Therefore, all these SK are non-null. Next, we define T1 equal to S1 by norm of S1. Then, since T1 is defined in terms of S1 and SKs are non-null, so this T1 is non-null vector. And norm of T1 is equal to norm of S1 by norm of S1, which is equal to norm of S1 by norm of S1, which is equal to 1. And linear hull of T1 is equal to linear hull of S1. We define this T1 in such a way that linear span of T1 is equal to linear span of S1. Next, we define P1 in V1 equal to S2 minus inner product of S2 comma T1. Next, take the inner product of B1 with T1, which will be inner product of, now put the value of B2, which is S2 minus inner product of S2 comma T1 comma T1. If I expand this one, I will get inner product of S2 T1. In this step, first we will get inner product of S2 comma T1. Okay. Since this is a scalar quantity, as inner product is a function from Cartesian product of the set to complex fields, so this S2 T1 can be taken outside, and this is T1 comma T1. Okay, so I will get this step. Since inner product of T1, we know that this is T1 norm of T1 square. So in the next step I will get this one as to T1. So in place of second term, in the next step I will write this one as norm of T1 is equal to 1. So norm of T1 square will be 1. So this is inner product of S2 comma T1 minus inner product of S2 comma T1, which is equal to 0. So inner product of B1 comma T1 is equal to 0. B1 is orthogonal to T1. Next, if B1 is equal to theta, then S2 is a scalar multiple of S2 is a scalar multiple. S2 is a scalar multiple of T1 comma T1. Now T1 is my S1 by norm of S1. So put this value T1 equal to S2 norm of, this is T1, keep this T1, here you should put S1 by norm of S1. Since S2 and S1 are scalar multiple of each other, so S1 and S2 are linearly independent set, which is contradiction because S1 and S2 being subset of this linearly independent set must be linearly independent. This contradiction arises because we have considered b1 is equal to theta. So by hypothesis, b1 must not equal to theta. This is the case. b1 must not equal to theta. Next, put t2 equal to b1 by norm of b1. Then we will get norm of t2 equal to 1. Next, check out what is the inner product of t1 comma t2. t1 is my s1 by norm of s1, and t2 is my b1 by norm of b1. Take in the next step, take this norm of s1 and norm of b1 outside. Here it is norm is a function from the set to real 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 number. So this 1 by norm of s1, norm of b1, not conjugate of norm of b1. Okay, because norm is a function from x to r. Inside the inner product, we will get s1 comma b1. Next, put the value of b1. What is b1? b1 is s2 minus inner product of s2 comma t1. Put this value. Put this value. This is your b1. Next, expand this. You will get this one. Within bracket, you will get inner product of s1 comma inner product of s2 t1. Since S1 and S2 are subset of a linearly independent set, so this inner product is my 0. This inner product is my 0, as S1 S2 is linearly independent set, and we know that every linearly independent set is orthogonal set, so they are orthogonal. We will left with this term only. Yeah, and by using the properties of inner product space, take this outside, as norm is a function from Cartesian product to complex field. So I can take here conjugate of this, that is inner product of S2 T1. Remaining will left as it is. This is 1 by norm of S1, norm of B1 minus will come down minus, then conjugate of inner product of S2 T1, inner product of S1 T1. This conjugate of inner product of S2 S T1 by using the property of inner product space, it is equal to this one. So in the next step, it is 1 by norm of S1, norm of P1 minus inner product of T1 S2, inner product of S1 T1. Here in the next step, put the value of T1, you will get this one, S1, norm of S1 this is my 0, so 0 into this will give you whole term 0, this one. Therefore T1 is orthogonal to T2. Also linear hull of T1 T2 linear is equal to linear hull of S1 S2. Thus T1 T2 is my orthonormal set. Okay, and linear hull of T1 T2 is equal to linear hull of T1 T2. Next, we define P2 equal to S3 minus inner product of S3 T2 minus inner product of S3 T1. Observe the pattern. Here my suffix is 2, suffix of S is 3, but suffix of T is 2, and here suffix of T reduces to up to 1. B2 is my S3, inner product of S3 T2 multiplied with T2 minus inner product of S3 T1 multiplied with T1. Now take the inner product of B2, inner product of B2 T1, inner product of B2 T1, B2 T1, which is equal to my inner product of, put the value of B2, that is S3 minus S3 T2 minus inner product of S3 T1 comma T1. If I expand this one, I will get inner product of S3 comma T1 Next, minus inner product of S3 T2 comma T1. Since this inner product can be taken outside, I can write this inner product of S3 T2, inner product of T2 comma T1 minus inner product of S3 comma T1, inner product of T1 comma T1. Since T1 and T2 is orthogonal, so this inner product is my 0. I will left with this one. Inner product of S3 comma T1 minus inner product of S3 comma T1 norm of T1 whole square. This is inner product of S3 T1 minus, since norm of T1 is my 1 square will give me 1. So this is my inner product of S3 T1 and this is equal to my 0. So I am getting a 0. That means B2 is orthogonal to T1. Similarly, I will get B2 is orthogonal to T2. If you proceed similarly as this one, as this one, you will get B2 is orthogonal to T2. That means B2 is orthogonal to my both T1 and T2. If I put T3 equal to B2 by norm of P2, then we will get norm of T3 equal to 1. Thus, we have an orthonormal set T1, T2, T1, T2, T3 such that linear hull of T1, T2, T3 is equal to linear hull of S1, S2, S3. That is linear span of T1, T2, T3 is equal to linear span of S1, S2, S3. We are going to prove by induction, mathematical induction. We have seen that result is true for n equal to 1, n equal to 2 and n equal to 3. We are going to show that this result is true. First we assume that the result is true for n minus 1. Then we will show that result is true for n. Hence, by mathematical induction, the result is true for any natural number. For that, we assume an orthonormal set T1, T2, Tn minus 1 in hex such that linear hull of T1, T2, Tn minus 1 is equal to linear hull of S1, S2, Sn minus 1. Linear hull is nothing but the linear span, where Tn minus 1 is equal to my Bn minus 2 and norm of Bn minus 2, where Bn minus 2, observing to the pattern of defining Bn minus 2, V2, that is S3, S3 T2, T2, S3 T1, T1, we define Bn minus 2, that is Sn minus 1, suffix is 1 more than V, inner product minus inner product of Sn minus 1, Tn minus 2, Tn minus 2 minus inner product of Sn minus 2, Tn minus 3, Tn minus 3 goes up to inner product of Sn minus 1, T1, T1. Next, we define Bn minus 1 as Sn. Inner product of Sn, Tn minus 1, Tn minus 1 goes up to minus inner product of Sn, T2, T2 minus Sn, inner product of Sn, T1, T1. Now for I ranges from 1 to n minus 1, we are going to check out the inner product of Bn minus 1 Ti. What is the inner product of Bn minus 1 Ti? This is equal to, put the value of Bn, that is Sn Tn minus 1 Tn minus 1 goes on, somewhere it will be Sn Ti goes on Sn T1 comma Ti bracket close. This is equal to inner product of Sn Ti minus. This will be inner product of Sn T n minus 1, inner product of T n minus 1, comma Ti. Okay, goes on. Inner product of Sn Ti, inner product of Ti Sn T1, inner product of T1 Ti. So this will give you inner product of Sn Ti. Since from this T1 T2 dot Tn minus 1 is an orthogonal set. So all this inner product is equal to 0. All this inner product is equal to 0. Only this term will leave this. That is this one. As norm of Ti is equal to 1, I will left with this one. This is equal to 0. So I am getting this one is 0. That means Vn minus 1 is orthogonal to T1 T2 dot Tn minus 1. Next we put Tn is equal to Vn minus 1, norm of Vn minus 1. Then norm of Tn is equal to 1. Then this Tn is orthogonal to T1 T2 dot Tn minus 1, as Tn is equal to Vn minus 1 and Vn minus 1 is orthogonal to all T1 T2 up to Tn minus 1. So this Tn is equal to, is orthogonal to T1 T2 dot Tn minus 1. Hence the set T1 T2 dot Tn is orthogonal set such that linear hull of T1 T2 dot Tn is equal to linear hull of S1 S2 dot Sn. Hence by mathematical induction T equal to T1 T2 dot is an orthogonal set, and from the construction of T it is clear that T and S have same linear hull, that is linear span. Hence the theorem. Next is example of Gram-Schmidt orthogonalization. Given the basis 1 0 1 1 0 minus 1 0 3 4 4 B3 are construct from it by the Gram-Schmidt process of an orthonormal basis relative to the standard inner product. Let us denote the given basis by B and its element by S1, S2, S3. That is S1 equal to 1 0 1, S2 equal to 1 0 minus 1, S3 equal to 0 3 4. The norm of S1 square is equal to inner product of S1 comma S1. That is multiply the element of S1 with S1, 1 with 1, 0 with 0, 1 with 1. That is 2. Next is norm T1. We take T1 equal to S1 by norm of S1. Now norm of S1 is norm of S1 square is 2. So norm of S1 is root over 2. So this is 1 by root over 2. Here S1 is my this element 101. That is my T1 is equal to 1 by root 2, 0, 1 by root 2. Next we divide P2, which is S2 minus S2 T1 T1. Now we have S2 is this element. We have T1. T1 is this element. To find out B2, we need to find out the inner product of S2 comma T1. Inner product of S2 comma T1. S2 is this, T1 is this. That is, multiply this element with this element, add up with multiplication of this element with this element, add up with multiplication of this element with this element. This is our, this is 0. So inner product of S2 T1 is 0. Put the value of S2. S2 is this, and inner product of S2 T1, which is 0, then T1, this is this element. We will get B2 equal to 1, 0, minus 1. And norm of B2 square equal to inner product of B2 comma B2, which is equal to, multiply this element with itself, that is 1 multiplied with 1, 0 multiplied with 0, minus 1 multiplied with minus 1, that is 2. This implies norm of B2 is equal to square root 2. Let T2 is equal to B2 by norm of B2. B2 is my this element 1, 0, minus 1. Norm of B2 square is 2. This implies norm of B2 is 2, root 2. So this is 1 by root 2. B2 is this element 1, 0, minus 1. So I will get T2 equal to 1 by root 2, 0, minus 1 by root 2. Next we define B3 equal to S3 minus inner product of S3 T1, T1 minus inner product of S3 T2, T2. To find out this value, we have S3, we have T1, we have T2. But we need this value, inner product of S3 T1, S3 T2. S3 is my this value 0, 3, 4, and T1. T1 is my this value 1 by root 2, 0, 1 by root 2. So put this value, multiply this element with this element, add up with multiplication of this second two element, add up with multiplication of these two element, we will get 2 root 2 on simplification. Again, inner product of S3 comma T2, S3 is my 0, 3, 4, and T2 is my this element, T2 is this element, 1 by root 2, 0, minus 1 by root 2, which on simplification will give you minus 2 root 2. Therefore, B3 equal to, put the value of S3, 0, 3, 4, and inner product of S3 T1, inner product of S3 T1 is this, minus of this, then T1, T1 is my this value, T1 is this value, put this value, then minus inner product of S3 T2. S3 T2 is minus 2 root 2, minus 2 root 2 will be plus 2 root 2. Then put the value of T2. T2 is my this value 1 by root 2, 0, minus 1 by root 2, which on simplification will give you 0, 3, 0. Now norm of B3, which is inner product of norm of B3 square, which is inner product of B3 multiplied inner product of B3 comma B3, that is B3 multiplied with itself, 0 multiplied with 0, 3 multiplied with 3, 0 multiplied with 0, 0 multiplied with 0, 3 multiplied with 3, 0 multiplied with 0. I will get this one. This is equal to 9. This implies B3 is equal to 3. And let T3 equal to B3 by norm of B3, which is equal to 1 by 3, 0, 3, 0. And this is equal to 0, 1, 0. T1 is my 1 by root 2, 0, 1 by root 2, and T2. T2 is my this one. T2 is this one. 1 by root 2, 0, minus 1 by root 2. 1 by root 2, 0, minus 1 by root 2. T3 is my 0, 0, 0, 1, 0, 0, 1, 0, which is the required orthonormal basis for B3 are corresponding to the given basis. Given basis this one. These are your home assignment. You should try to solve this. In case of any problem, you should inform me. I will solve it for you. With remaining will be in the next class. With that, I would like to conclude. Thank you.